Good afternoon and welcome to Big Science with Small Satellites. If you have questions for the speakers during the session, please enter them into the chat feature. And now we are pleased to welcome our moderator, Shandy Asturias, Launch Service Manager for Virgin Orbit.
Thank you so much for the introduction. I'm really excited to be able to host this panel, and I think we have some amazing panelists that are playing some key roles in the small satellite industry. I think we'll be able to provide some insights that we'll all find interesting and very valuable. So let me start by introducing all of our panelists. First, we have Dr. Carrie Cahoy. Dr. Carrie Cahoy is an associate professor of aeronautics and astronautics at MIT and leads the MIT Space, Telecommunications, Astronomy, and Radiation, the STARS Lab. There she develops nanosatellite laser communication systems and weather sensors, such as the micro-sized microwave atmospheric satellite, MicroMass, and the microwave radiometer technology acceleration, the MIRAT mission. Cahoy also supports space telescope missions, such as the Wide Field Infrared Survey Telescope, the WFIRST, to directly image exoplanets, and is developing a 6U CubeSat to test MEMS deformable mirror technology for high contrast chronograph wavefront control systems. STARS Lab research also focuses on understanding space weather, identifying when spacecraft are affected by anomalies due to interaction with energetic particles, and improving their performance and reliability, including performing on CubeSat components. Her doctoral research was on radio occultation studies of the upper atmosphere of Mars using the Mars Global Surveyor spacecraft and on the MIT Gravity Recovery and Interior Laboratory Lunar Mission Team at NASA Goddard Space Flight Center. Our second panelist is Dr. Craig Hardgrove. He is an assistant professor in the School of Earth and Space Exploration at ASU. Dr. Hardgrove is the principal investigator for the Lunar Polar Hydrogen Mapper, LUNA-HMAP, CubeSat mission. He is also a participating scientist on the Mars Science Laboratory Curiosity rover, Dynamic Albedo of Neutron Instrument Team. Dr. Hardgrove's research is focused on the characterization of hydrated rocks and their constituent phases on rocky planets through the use of nuclear spectroscopic instrumentation, as well as on small spacecraft development for interplanetary exploration. Dr. Hardgrove is active in several NASA instrument development projects and has over a decade of experience working on spacecraft missions, having begun his career working on the Mars exploration rover Spirit and Opportunity. In addition to serving as a principal investigator for LUNA-HMAP, Dr. Hardgrove is currently a member of the science team on the Bepi-Colombo mission to Mercury, as well as Curiosity and Mars 2020 Perseverance rovers. He earned his doctoral degree in geology from the University of Tennessee, Knoxville in 2011, and his Bachelor of Science degree in physics from Georgia Institute of Technology in 2005. Dr. Scott Rafkin is our third panelist. Dr. Rafkin is a program director at the Southwest Regional Research Institute, SWRI, in Boulder, where he leads the research and hardware projects focused primarily on the study of terrestrial planetary atmosphere, including Earth, Mars, and Titan. Dr. Rafkin is the project scientist for the Mars Science Laboratory Radiation Assessment Detector and a co-investigator on the Mars 2020 rover Perseverance and the Dragonfly rotorcraft mission to Titan. Dr. Rafkin is currently developing laser spectrometers for the in situ characterization of planetary atmosphere and is the principal investigator of several proposals currently under development to study the atmosphere of Earth and Mars with LIDAR. Imaging radiometers, and other satellite remote sensing instrumentation. Dr. Rafkin earned his degree in atmospheric science from UCLA and Colorado State University, where he earned his PhD in 1996. After his PhD, and prior to his arrival at SWRI 18 years ago, Dr. Rafkin served as a postdoctoral student at the University Corporation for Atmospheric Research and as an assistant professor of meteorology at the San Jose University. And last but not least, we have Ms. Florence Tan. She is the chair of the Small Spacecraft Coordination Group, SSCG, at NASA headquarters. She's also the Deputy Chief Technologist for NASA Science Director at SMD. In her role as SSCG chair, she leads the SSCG to coordinate and develop NASA strategy and vision for small spacecraft in science, exploration missions, and technology activities. As the Deputy Chief Technologist for SMD, she supports the SMD Chief Technologist to survey and assess technology needs for NASA science. Previously, Florence worked as a lead electrical engineer, designer, INT engineer, manager, operator on missions to Mars, Saturn, Titan, and the Moon. Florence has received numerous awards, including the NASA Medal for Exceptional Achievement, the Robert H. Goddard Exceptional Achievement for Outreach, Goddard Division Excellence Award, the NASA Honor Award Silver Achievement Medal, and others. Florence holds a Bachelor of Science in Electrical Engineering from the University of Maryland and a Master's of Science in Electrical Engineering from Johns Hopkins University, and also an MBA from Johns Hopkins. So we have they're amazing panelists. So before we dive in, I want to set the stage a little bit for our conversation. From the launch of the initial satellite Sputnik to today, we've seen a considerable amount of evolution in the development capability, size, cost, the lifetime of satellites. And small satellites are no exception. We can see how dramatically that they have matured over the last 2 decades. We now see a standardization in form factor. And now we also see a wider industry acceptance of small satellites. These small satellites are proving mighty, especially in their application for cutting edge science and exploration, as you will hear about from our panelists today. Today, small satellites are playing an increasingly important and interesting role in Earth observation, climate and weather monitoring, and even space sciences such as astrophysics. For instance, the JPL RAINCube mission proved that you can study Earth's precipitation using radar on a 6U CubeSat form factor. It is performing science that traditionally had been performed by much larger and much more expensive spacecraft. We are starting to see the same trend in deep space exploration. For example, 2 years ago, NASA's Marco CubeSats provided communications and telemetry relay to the InSight lander as they passed by Mars. These were the first CubeSats to operate beyond Earth orbit, and they were successful. That success really allows us to look at distributed and constellation architectures in a different way. And it allows us to really envision how these microsats can participate in a wider array of missions. And that's not all. NASA is now looking at small satellites to be a component of its lunar exploration goals. An example is the Luna HMAP mission, a spacecraft the size of a large shoebox, which will measure where and how much water ice is hidden in the lunar South Pole. Also, sometime next year, the NASA Capstone spacecraft will test out innovative near rectilinear halo orbits in support of the Artemis program. That mission will not only demonstrate how to enter into and operate in this orbit, but will also test out new navigation capabilities along with the Lunar Reconnaissance Orbiter spacecraft. These are just 2 of several small satellite missions currently in development for lunar exploration. And there are several proposals being worked on for small satellites to other distant worlds like Venus, which has been in the news recently with some exciting announcements. Clearly, NASA has been leaning in on small satellites playing a bigger role in the exploration of space and leveraging the big science that they can provide. That's why we're excited to have our experts with us today for discussion on the remarkable present and the exciting future of the role of small satellites in science and exploration. So with that in mind, I want to turn to our panelists and ask each of them to tell us a little bit about some of the things that they find interesting in the small sat industry. So let's start with Dr. Cahoy.
Thank you, Shandy. Can you hear me okay?
We can hear you.
Okay, thanks for the great introduction for everyone. You brought up lots of exciting progress in the field of small satellites for science research, and wanted to talk a little bit first about some of the projects that I have going in my lab, and then about a couple of the things that would be game-changing moving forward in the field. So in my lab right now, some of our missions that we currently have a DARPA project on orbit called the Deformable Mirror Demonstration Mission, which you mentioned in the context of exoplanet imaging and some of the astrophysics telescopes like WFIRST, which is now the Roman telescope. It's been officially given its name. And so that 6U CubeSat that is in collaboration with Aurora Flight Sciences, which is a Boeing company now, and the bus was built by Blue Canyon Technologies, has a payload on it that was built by graduate students and undergraduates in my lab and postdocs, with a little mini telescope that's testing a small microelectromechanical deformable mirror that is used for adaptive optics on the ground and wavefront control in space for space telescopes. to be able to make high contrast images of planets around other stars. And so we were excited that, we launched to the ISS in February. We finally deployed in July and got on orbit, and we've gotten our first data down showing that the mirror does work as expected on orbit, which is great news. As we're going through this mission and previous missions, communications with the ground has always been a challenge. You would think that we have radios and have this down by now, but 10-minute overpasses in low Earth orbit, if you only have one ground station at your disposal, is very challenging to get a lot done during. High data rates make a big difference, solid connections make a big difference. And to that end, we've been working both on radio and laser communication systems to help improve the challenge and bottleneck in getting data from space to the ground, especially as you're saying, the instruments are getting more exciting. There are people doing radar, there are people doing all sorts of multispectral and hyperspectral imaging. And so we want to be able to get these large volumes of data down and still be able to do so power effectively. CubeSats don't have very much power. You can't put enormous solar panel arrays on them, and you also can't carry enormous batteries for when you're in orbit night. So having compact communications terminals is something that we really want, and spectrum licensing and being able to get bands in the radio frequency spectrum that are allocated for CubeSats when there's so many commercial players in the game is challenging as well, especially for high bandwidths. So we've looked to free space optical communications and laser communications to help mitigate some of this. And so we have some very exciting missions coming up with NASA, working with NASA Ames Research Center and the University of Florida to test laser communication systems for CubeSats that use small microelectromechanical fine pointing systems, and we'll be demonstrating downlinks and crosslinks. And our way around hard to access ground stations is to use commercial products like amateur astronomy telescopes to receive the laser signals from space. And so we'll be working on implementing that and demonstrating that with this mission. It's called the CLIC mission. So the CubeSat LaserComm Intersatellite Crosslink mission, which should be launching in the next year and a half. So there's a downlink 1, CLIC A, and then there's 2 crosslink ones, CLIC B and C, that we're working on. So that comms is one of the hard parts. One of the other hard parts that I think is where Virgin Orbit comes in really, and will play a big role, is getting to the exact orbit you want, where you want and when you want. And so we have some missions that we're working on right now that are based off of some of our precursor missions that do weather sounding. The mission that I'm partnering with now with Dr. Bill Blackwell at MIT Lincoln Laboratory and his very extended team that includes lots of affiliates that would probably take the whole 10 minutes to mention and credit properly. But they're building a constellation, again, using Blue Canyon platforms, microwave radiometers that can take atmospheric temperature measurements but see through clouds, so that you can get really meaningful inputs into your weather forecasting models for things like storm tracking or hurricane tracking. But you want a global constellation of these, and to have a global constellation, you need things in multiple orbit planes around the Earth. And at the moment, the only way to really get a small sat into multiple orbit planes is to have multiple launches, so that you can get the satellites in each orbit plane. It's very expensive in terms of fuel that at least a CubeSat or a small sat could carry on board to try to get yourself from one orbit plane to another and change your inclination. So one of the real advantages, I think, to plans like what Virgin Orbit is doing for air launch is to be able to get some of these more cost-effective, highly productive small satellites that can do really good science to the orbits that they need to get to, so that they can make the revisits and the coverage that they need to make. And so we're looking forward in the future to having capability both from air launches, and then maybe more distributed ground launches with companies that have smaller rockets that have different types of launch sites at different latitudes that can reach those inclinations more effectively and provide that diversity for global constellation coverage and high revisit times. They want to go over the same spot on Earth every 15 minutes or better, which is hard to do right now. So those are some of the weather sensing missions that we're working on right now. And then we're also working on missions for ocean imaging and testing on-orbit calibration targets for optical imagers, and looking at using some commercial chipsets to do on-orbit image classification and autonomy, and also to do on-orbit data management. So sending data from satellite to satellite, tasking different satellites with different types of observations, and then eventually coupling those to on-the-ground models and on-the-ground needs that the models have, where the models can identify less accurate or less well-populated regions, and then autonomously task the satellites to find amongst themselves the next best observation and make that happen. So some of that software and planning and autonomy work is of interest and things that my group is working on. My group's about 30 students and a couple of postdocs and staff large right now. MIT has a new AeroAstro Small Satellite Center that myself and Professor Ali Dweck are co-directors of, that we're kicking off, and we're very excited about that, especially as across the Institute, people are becoming more creative and more innovative and coming up with great ways to use CubeSat and SmallSat payloads to achieve science and improve coverage in space and time around the globe. We're also now starting to brainstorm ways to get mass spectrometers to Venus to look at some of this phosphine that Professor Shara Seeger was speaking about the other day. And so there's no shortage of fun things to start thinking about payloads for and collaborations to form going forward. So I'll just end there, but I'm looking forward to hearing the other speakers. We have a great group of people.
Thank you, Dr. Hoy. That was a pretty amazing introduction. And I do actually also very much love your discussion of a lot of the problems that you guys are running into and how you're solving them. Because I think what I love about CubeSats and small sats is that democratization of space and just how everybody starts to have that access. And it's really intriguing and interesting on, you know, some of the creative ways that you're going to find to solve a lot of these problems that maybe corporations they don't run into the same problems. And I really think that everybody, small sats, whether they're students or companies or NASA missions, I think they can all really benefit from some of the solution finding that you guys are pioneering. So that was really interesting, and can't wait to dig in a little bit more into some of what you mentioned during the Q&A. I'll turn this over to Dr. Craig Hardgrove now for his comments.
Hello, can you hear me? Hello? Hello?
Yes, we can hear you.
Okay, sorry.
No problem.
Yeah, I think that was a great intro, and I would echo many of the things that Carrie said in our group. As you mentioned, I'm a planetary geologist, and the LunaMap mission is, like you said, the size of a large shoebox. Our total spacecraft mass is 14 kilograms, and one of the really interesting things that I think about in terms of small sats and micro sats, whatever you want to call them, for planetary science and going out beyond the Earth, is how these very small satellites will find a space to exist in the portfolio of NASA missions. And you know, NASA missions to Mars and other planets are sometimes few and far between, and so it becomes a question about risk tolerance, and so it also becomes a question about technology at that scale. So You'll likely hear from other panelists about ESPA class satellites, and those are very capable, and there are existing technologies that are quite capable of performing science missions at other planets at various TRL or technology readiness levels. But at these very, very small scales, the 6U scales for planetary exploration, where we have to propulsively maneuver around another planetary body and communicate in deep space with Earth, and have a science instrument that's capable of making the measurement that we need to. All of those technologies are at a lower readiness level in many cases. And so in our lab at ASU, one of the first things that we were tasked with on the LunaMap mission was creating a neutron spectrometer for planetary science that was capable of making the measurements that we needed to at the moon on a 6U spacecraft. And so as part of the mission, that was also part of the development effort. And there are existing neutron spectrometers that have flown on other planetary missions, but because our spacecraft was so small, we needed something that was highly efficient and could be matched with the form factor of a 6U so that we can achieve the science requirements for the mission. And so in doing that, we developed the spectrometer and we made it modular in such a way that for future CubeSat missions, smaller or larger, this type of instrument could be modified relatively easily to operate on other missions. And so that was one of the initial challenges. And I think other researchers around the country, like Carrie mentioned, there are all sorts of technologies that need to be developed to support these very small missions. And some of the challenges are a little bit different in interplanetary exploration, particularly in the realm of propulsion. I'll also just, I guess, briefly mention, we've identified water on the moon some time ago in various forms and distributions. There are two missions, the Lunar Reconnaissance Orbiter mission and the Lunar Prospector. They both carried neutron spectrometers. And one of the advantages of a neutron spectrometer is it gets the integrated 1 meter hydrogen content, or water equivalent hydrogen is what we call it. The neutron detector can't tell you whether or not it's water or some other hydrated phase, but water is most likely what's at the poles of the moon. And so these two missions orbited from between 35 and 50 kilometers above the south pole of the moon and made measurements with neutron instruments and identified these enrichments of hydrated phases around permanently shadowed regions of the south pole of the moon. But it's one of the few techniques that can get the bulk distribution down to about 1 meter. Other instrumentation can tell you just the optical depth. So if there's a frost at the surface and it's hydrated, but the neutron detectors can really get at the bulk. And that's an important element to understand how hydrogen's been distributed across the moon over geologic time, as well as for resources landing on the moon in the future and using water as a resource. We need to know that it's there in some bulk quantity. And the reason I'm bringing this up is that LunaMap, as a one science instrument, 14 kilogram spacecraft, will fly at altitudes of, on average, for our 141 orbits, about 10 kilometers over the south pole of the moon. And no spacecraft with a plethora of science instruments and $100 million or more budget would do that. So that's a mission profile that's ripe for a very small mission with one instrument. And I think the thing that's very exciting to me about these types of missions for planetary science is that I think very creative people in the future will be able to identify other types of missions like that, where there's a high risk, high reward science opportunity at other planetary bodies, where a small science mission can ride along with the primary mission and complement the data. So I sort of view LunaMap as, I really wish we could have flown along with LRO or Lunar Prospector, because our data wouldn't be required to interpret the data from LRO or Lunar Prospector, but it sure would have helped put some of the data in context, and it would have helped illuminate some things about what's going on with the distribution of water at smaller scales. So I think in the future that there's a really niche opportunity for these very small satellites that are capable of conducting these high risk, high reward science missions and riding along on all sorts of larger mission opportunities, which I think we need. So we really need all shapes and sizes in planetary science, but what I'm hopeful for at these really small sizes is that there's a niche for them in planetary.
All right. Thank you so much for those remarks. That's really exciting what you're doing. And I thought your comment was really interesting about the high risk, high reward. So I definitely want to come back to that because I think that definitely gets to the heart of what a lot of these microsatellites are capable of, and something new and unique that they bring to the table that perhaps we didn't have access to thinking about things in that sort of way before because of the size or the cost or the lifetime or other things associated with some of the larger spacecraft. So thank you very much for your comments. That was fantastic. I'm going to turn things over to our third panelist, Dr. Scott Rafkin, for his comments.
Hello. Hope you all can hear me and see me. We are entering a new revolutionary age, I believe, of science and planetary exploration that is enabled by a nexus of technologies and favorable programmatic environments. As a scientist, of course, very, very interested in the potential for the improved science return from these. But as a program director, I'm also keenly interested in the programmatic and technical environment that has to be in place to achieve that science. And so I'd like to touch on a few of these, both programmatic and science topics. First and foremost, there is a miniaturization of instrumentation. Payloads with capabilities that could previously only be hosted on large full-size satellites now have come into existence, and they can be accommodated on small satellites. By small, I mean things that are small enough to be hosted on secondary payloads, for example, on an ESPA ring, or down to on a CubeSat deployer like a P-pod or something like that. It could also be those that are small enough to be launched as a primary payload on modest commercial rockets like Virgin Orbit's, instead of having to require the full lift capabilities of a traditional expendable launch vehicle. So it's a growing capability of these small payloads that's really a motivator for these small satellites. Secondly, the small satellite launchers, the instrumentation that goes on them are also being enabled by new technology. I think the 3D printing and additive manufacturing techniques that have come about are just amazing. They reduced cost while still allowing you to meet mission assurance requirements. And in a lot of cases, they allow you to manufacture complex hardware pieces that you couldn't even previously machine. And so now we're able to open the door to really creative engineering and design solutions that continue to drive things to smaller packages, right? So that the ability to put more capable instrumentation on more capable and smaller rockets and satellites and buses is really coming to fruition. And programmatically, this is the third thing I think that's important, is that there's a growing acceptance of the smaller commercial vehicle launch options by NASA and other customers as a viable and cost-effective way to achieve mission success. These provide substantially greater flexibility than hitchhiking a ride as a secondary ride-along payload. You can actually be a primary payload now, and this gets you, as others have already mentioned, to go when and where you want to go exactly. And that allows you to eliminate risk and cost, and a lot of times the engineering that you need to do to host 2 or more unrelated payloads on a single launch vehicle. There's also an acceptance of smaller launch payloads as a recognition of their power and benefit to program resiliency and sustainability, right? So if you get a failure or an unrecoverable anomaly on a launch, deployment, or operation of an instrument on a single large satellite, it's expensive and it can end a program. And minimizing the potential for these types of failures on these large missions is expensive. And in contrast, the small satellites, they provide, in principle, resiliency, the ability to recover much more easily from the loss of a single satellite or a payload or an instrument, especially if it's a constellation mission, because oftentimes your science and data can still flow from the small satellites that remain. And the development time and cost to replace a single small satellite is far more digestible to a program than $1 billion plus single satellite mission. So that's just some of the, I think, synergistic and intersecting technologies and programmatic environments that are going to propel this satellite revolution forward. There's one more incredibly important element, and that's the unique science that can be done from small satellites. I'm convinced that even in the absence of unique science, the small satellite revolution has begun and it's underway. But I really also believe it is unique science enabled by small sats that's going to turbocharge this revolution. There quite simply is some science that can only be done with multiple science observatories, and small sats are perfect for this. These multiple observatories are, as I say, only achievable programmatically in the form of small satellites. Sure, you can launch a constellation of giant buses, but it's a lot of money and it's a lot of risk, and there's no need for that necessarily. So you can look at, for example, the first NASA Earth Venture mission, the Cyclone Global Navigation Satellite System, CYGNSS, that has a constellation of 8 small satellites that analyze direct and scattered GPS signals to infer the winds at the ocean surface. That constellation is necessary to achieve that science. And could you have done it with traditional large satellites? Technically, yes. Programmatically, probably not. Another example is the polarimeter to unify the corona and heliosphere. That's the PUNCH mission, which was recently selected as a NASA Small Explorer. And that's got 4 small satellites in a constellation to generate composite images of the corona and heliosphere. And so in both CYGNSS and PUNCH, this unique science is uniquely enabled by small satellites. There's really no other way to do this. So we can talk about small satellites being complementary to primary and larger missions, but I think there's also a recognition that they provide their own value in of themselves. I'm currently leading the development of an effort for some Earth atmospheric science with a constellation. I can't go into details because I'm still immersed in this highly competitive proposal process, but I can say that the science that we're looking to achieve, again, is unique. It cannot be done by a large satellite implementation. It's something enabled uniquely by small satellites. And finally, I'll just point out, this unique science goes beyond Earth. It's not uncommon for large planetary missions to have launch performance capabilities that are sufficient for small satellite ride-alongs. In the past, those resources went unused. The Mars Q1 Marco was hitched a ride on the Mars Insight Discovery mission. And I think that was the first and really great demonstration that good interplanetary things can come in small packages. It didn't do any primary science, but it certainly supported the entry, descent, and landing of the primary payload, which allowed that payload to provide key, unique science about the geophysical interior of Mars. And now we have the NASA Simplex program, which is sure to bear some scientific fruits with small satellites, both at Earth and beyond Earth's gravity and the space weather environment. The future is bright, but I think there are still challenges, some of which have been mentioned. The small launch options are still not fully embraced, and that limits our ability to take advantage of small satellite science. There are budgetary and other pressures that can squeeze the small satellite programs. In fact, just this morning, NASA announced a delay to the next Simplex opportunity indefinitely. But to balance that, there are very positive signs. The next Earth Venture mission, Earth EVM3 from NASA, is now again going to allow non-NASA launch services. Okay, so NASA is recognizing the value here. And hopefully these opportunities are going to become standard and routine. We won't even have to think about whether they'll be included or not. There are unique challenges for deep space small satellites. Surviving and operating in deep space is a whole different animal. It's going to require advances in propulsion, attitude and control system, thermal management, power management, and communication. None of these are insurmountable. Lots of really smart people are working on them, but it's going to take the will and desire of NASA and other agencies, almost certainly in partnership with the private sector, to continue to mature and demonstrate these technologies. And the sooner that happens, the sooner we will reap the scientific benefits that come from these small satellites. It's not a matter of if, but how quickly it's going to come. It's going to come, and it's going to be revolutionary. Thanks.
Thank you so much. That was fantastic. Yeah, I agree. I think the small sat revolution definitely has started, and it was great to mention also, not necessarily just from a technical perspective, but from a programmatic perspective. This really is a bit of a game changer and does allow you to programmatically go out and seek different types of missions and accomplish different types of successes. So yeah, I have a few questions lined up for that to touch on that, because I think that that's also a really unique part of the CubeSats. Thank you very much for your comments. And lastly, I'll turn it over to Ms. Tan for comments.
So I'm going to try to turn on my camera. Can you hear me?
We can hear you.
See me. Okay. Hi. Thank you for hosting this really exciting talk, and my fellow panelists. You said it all, so it's a good thing to go last sometimes. So in the last 5 years, certainly, the growing and establishment of access to space, by the industry, the increase in innovative miniaturized instruments, and the measurements we can make, and all the different revolutionary, flowering of technology that allows us to access space much easier. That has really definitely prompted NASA to look at small spacecraft as a important a part of a balanced and integrated portfolio for science exploration. We certainly noted that Dr. Thomas Zurbuchen, his thinking inside the box report from the National Academies, that influenced us. And so we understand that there is a huge role for a small spacecraft to play. It's certainly big spacecraft is not going away. It's just that small spacecraft is now coming into its maybe the time in the sun. So we have certainly, as Scott mentioned, we understand that we can use survey missions, these point and stare, to look at all sky surveys or exoplanet observations in astrophysics from LEO and GEO. We can look at Earth measurements, long-term continuity measurements, like CSIM and CTIM for Earth science, and heliophysics as well, for space weather measurements, and these kinds of simultaneous multi-point measurements that can only be observed as from the boundaries of Earth and space for heliophysics is so key to our understanding of space weather. Those types of things, measurements could not be done, I would say, with just one. We want to have multiples to look at the spatial and temporal measurements that come with the use of multiple spacecraft. And from deep space, I know Craig mentioned ESPA class spacecraft. The reasons being you could use ESPA class spacecraft, larger spacecraft, to carry additional propulsion, higher power communications, larger instruments that will make that capability so much more available. Imagine being able to send a small spacecraft along with Cassini, where we had to wait till we had the grand finale to make these discoveries that Cassini made towards the end of its glorious dive into the Saturn, and being able to observe planetary magnetospheres, atmospheres, surfaces, so compelling. So I really think that there is a place in small spacecraft, and especially in deep space, ESPA class spacecraft. I chair the Small Spacecraft Coordination Group for NASA, and this was we are interested in small spacecraft issues, and we meet regularly, and we're an APMC chartered entity, and we serve the Science, Human Exploration and Operations, and Space Technology Mission Directorates administrators, associate administrators on any kind of cross-agency policies and programmatics that come with small spacecraft. So we also have representatives in NASA centers, headquarters, and mission directorates. And so I think that for us as a body, we are very interested in trying to collaborate and figure out what policies that would advance the state of the adoption, I would say, and full embrace of small spacecraft for our science, exploration, and technology goals. So we have 4 cross-cutting themes that have been identified. Last year, I released a strategic plan for small spacecraft at SmallSat, and that is high priority science, support to human exploration, disruptive technology innovation, and regular access to space. And the plan outlines the strategies to advance these themes. And during this time, since the strategic plan was released, we have honed in on certain focus areas that would be very, very important to make this supportive ecosystem for small spacecraft. And we are continually trying to understand what strategy and implementation we need to look at. Of course, to make the science a reality, we need reliable hardware and technical excellence. We need the right services and infrastructure in place. We need to have, with SPD5, for example, security and enterprise protection. We have, of course, launch accommodation that is necessary to access space, and perhaps ride share if necessary. And our international partners and commercial partners are part of the equation in making sure that we are able to have that environment that would foster the adoption of small spacecraft as a balanced portfolio for science and making new discoveries. So with that, certainly within NASA itself, besides creating the small spacecraft coordination group and making this active coordination possible within our mission directorates, NASA Science Mission Directorate has also established a rideshare office led by Ali Mendoza-Hill, again to foster ESPA class payload as our missions are developed and built. So we as a group are very aware. I know that my fellow panelists have much more different ideas that I hope to hear and learn during this panel. So with that, I give it back this time back to you. Thank you.
Thank you so much, Ms. Tan, for those comments. It was very interesting to see how a lot of the comments from the first 3 panelists really aligned with a lot of your comments in terms of how NASA is handling this. So it's really great to see that come together. So a couple of questions to come up on that. To kind of start us off on the conversation, I wanted to turn first to Dr. Cahoy. One of the things I know that your lab works on is related to radiation, and it's a major concern for satellite missions, and it is something that is considered in all the satellite components. Are there different considerations for radiation proofing small satellites versus the traditional larger satellites? Is there a different risk posture perhaps there? And I know that could perhaps be dependent on if you're doing something near Earth or deep space, but what has been your experience with that on the satellites that you've done?
Thanks for the question, Shandy. Yeah, so most CubeSats are in low Earth orbit where the radiation environment still plays a very significant role, but not as terrifying as it could be if you were at higher altitudes in the radiation belts. where say the global positioning satellites live on a regular basis. So you don't have to build your satellites to necessarily be radiation hardened. You do want critical systems still to be radiation tolerant. On the larger satellites, there are multiple ways to handle radiation. Shielding, so physically putting metal or mass between, or tantalum between yourself and the thing that, and radiation, so the component that you want to protect. So that's one way, but you have to have enough volume and ultimately launch lift resources available to do that. You also on some of the larger missions tend to do redundancy. So you'll have duplicate systems. And so if one goes down because of radiation upsets or damage, you will switch to your backup system, and maybe you'll have that implemented and can do that with all of your subsystems or even your payloads on a larger satellite. On small satellites and CubeSats, you really try to single string where you only have one copy of a thing at a time as much as you can. That said, there are key subsystems that you may need and may want to have duplicated for being able to stay up despite radiation effects on your satellite. So full bus power cycles and having watchdogs in place to look for stalls and activity are really important on small satellites. And developing operational plans that are tolerant to things maybe having to power down on maybe not daily, but maybe bi-weekly basis, just to clear out some of the bit flips that you might have had happen due to radiation. You almost always want to have a backup communication system, one way or the other, so that you have a way to get in to your satellite and, if necessary, power cycle a subsystem or component or command a full bus reset. So those are the ways that small satellites typically do radiation management. You also will have more watchdogs and more resets and capability in your command and data handling system to keep an eye on your payload and what's on and off, and what's telemetry might be stale or not changing and not responding, and be able to power cycle those. So those are some of the approaches. You do still try to keep copies of a golden copy of your flight software in multiple places, so that if for some reason there's issues with bit flips in the memory where your software is actively being used, you can reprogram it on reboot. If you try to keep rebooting and it's still not coming up, then you have this fallback to reprogram to one of these copies. That you may have a voting process to make sure that that one is good too, before you try to reprogram it. CubeSats in general will try to spend less on radiation hardened components that are usually more expensive. They're very robust, but they may be less capable than the best technology out there. People often joke about, if I could only fly my cell phone, you know, so some of the radiation electronics out there are not quite that capable. And so you come up with these kind of operational and software-based fault detection systems that you try to implement on your CubeSats to manage that.
Yeah, I can imagine that also helps with part selection and lead time associated with some of the items that are more radiation hardened. Helps you with mass, control mass as well. So along kind of those lines, Dr. Hardgrove, you had mentioned the high risk, high reward. What are some of the things within CubeSats or within your Luna HMAP mission that you are seeing where you can take risks? What are those risks that you are taking, and what are the rewards that you're obtaining from those risks?
Sure. Yeah, the primary one is the one I mentioned about achieving a lower altitude orbit. So we can just fly between 10 and 15 kilometers over the South Pole using and to make a neutron measurement. So that's baked into the mission profile as a risk. And you know, we work with Kinetics, which is a company that does the mission navigation design for the New Horizons mission and the OSIRIS-REx missions. They have a lot of experience navigating spacecraft in deep space, and so they have confidence that we can achieve those altitudes successfully. And some of that's going to depend on the performance of the overall spacecraft system in space. So we are not able to, in some cases, fully characterize all of the components on the ground due to the limitations of our program. So we characterize the fundamental critical mission phases and make sure that everything's working in an integrated way for all of the critical mission scenarios. But there are some elements of the mission that we're unable to test. And I think that, in coordination with our NASA representatives, everyone feels that given the restrictions on the program and where we fit into the overall suite of the mission budget and profile, and the fact that we have already built the spacecraft, and so it's all together on a shelf, everything is functional. If we were to encounter some issue, that we've already demonstrated a path.
Oh, we might have lost Dr. Hardgrove there. I'll give him another second to see if he comes back online. All right, we'll see if he comes back online. In the meantime, I'll swap my question over. We'll come back to wrap up that question. I'll turn to Dr. Rafkin. You're a planetary scientist and you have a deep background in atmospheric investigation. Do you see small satellites being able to achieve robust atmospheric space studies? And part of where I also want to direct that question is I'm kind of also curious about not only the capabilities, but the size maybe associated with those capabilities. Like, for example, can a 3U or 6U go to Venus and accomplish real science missions? Or do you need something more ESPA-sized because of power considerations? How does the size fit into that as well?
Yeah, so yeah, clearly, I think absolutely small satellites have a role to play in atmospheric studies, both here on Earth and at other planets, other planetary bodies. I guess there's sort of two roles, right? I mean, one is we can think of it as complementary missions, as ride-alongs, sort of like what Marco did with the InSight mission. If you want to go to Mars, there are most definitely payloads that could ride along and either support those primary missions or do science in their own right. I think for the interplanetary missions, the small size is a particular challenge, particularly attitude and control systems, for example. Often, on Earth, we can use magnetic torques and things like that. We don't have those out in interplanetary space. So if you want a spacecraft that can, maintain its orientation and also move around a little bit and do its own thing, it's harder to get that in a small package the farther you get out away from the sun. The solar flux goes down. You need bigger solar panels. Communication is a really tough one in a small package at Mars. You have limited power, and the smaller your spacecraft, typically, the lower your power is. You're far away. Your antenna is typically a little bit smaller, but you're oftentimes still generating lots of really good data. So being able to get that back is a challenge in small packages that you see as you get out to Mars and perhaps beyond. So I do think there's a little bit of a size scaling that goes on. You can do really great things in small packages in 6U or 12U maybe, or even smaller at Earth or at the Moon. But as you start to move out, the propulsion, the attitude and control, the communication, the payload itself, I think all starts to drive you to slightly larger, generally starts to drive you to slightly larger sizes. I don't think that's a universal truth, but that's sort of been my impression as I've tried to think about what I'm going to do at Earth versus what I can do at Mars.
Thank you so much for that. And I think Dr. Hardgrove, your connection is back on.
Yeah, can you hear me?
Oh, well, welcome back. Kind of to keep going on that, you mentioned that, you guys have the 141 orbits and you get to 10 kilometers above the location that you want to observe. Has that allowed you to take other risks in terms of, or has that affected your design strategy in terms of, you know now what your lifetime capability is, so it's not like you have to make this CubeSat last 10 years. You have, a very specific lifetime that you're targeting. How has that changed your design?
Yeah, I think, Carrie mentioned some of the radiation effects. And so we sort of have a design requirement for, 10 kilorad total ionizing dose on all of our components. And really the science mission is not the driver in terms of the mission life. So our propulsion system it's an ion propulsion system. It's about the size of a tissue box that you'd have on your kitchen or your living room table. And it provides less than a millinewton of thrust. And so our ability to get into lunar orbit is dominated predominantly by the Earth, Moon, Sun position at the time of the Artemis 1 launch. And so depending on the month that we launch, which is to be determined right now, it can take us anywhere between 6 months and a year and 2 months to get into the science phase, which is only 2 months long. So really the bulk of the mission and the science orbit is a frozen orbit. So we only need statistical corrections to the orbit once we've achieved that highly elliptical science orbit with paralleling over the South Pole. So the mission drivers are primarily on these long thrust arcs, deployment from SLS to lunar capture and transition into the science phase. So those were the primary drivers, and we sized the solar arrays accordingly, and the radiation of the spacecraft. We have all of the watchdogs that Ray mentioned in place for any upsets that may occur during these long thrust maneuvers with the propulsion system, as well as flight software. We have redundant hard drives and things, solid state hard drives that stave our data. So a lot of that mission profile was baked in, but the driver actually wasn't the science orbit. It was the fact that the propulsion system is low thrust.
Yeah, that's very interesting, because I know that for a lot of CubeSats, some don't have any propulsion. When you do have propulsion, that becomes, a key part of the design and sometimes the limiting factor. So that's a great point to make. My next question I'll direct to Ms. Tan. I am curious to know about, how NASA's view on small sats and microsatellites has changed over the last 1, 5, 10 years. What sort of policy changes do you see? So for example, you mentioned that there was a new rideshare office. What other changes have you seen come about that you feel like are encouraging for small sats? And what other things do you feel like are still missing and you really want to see in place?
So I think about the small sat community we serve as, trying to enable the pieces that will build the measurements that we need. So from that point of view, the science community is already very creative in making many types of measurements using the technologies that are out there now. However, certainly we've been talking about propulsion a lot, right? And there's all these different technologies that we have to solve. So in the next 5 years, having a ESPA class rideshare office at SMD is certainly important because we're trying to take advantage of the capacity of our launch vehicles that we're going to be flying and hopefully bringing our small sats along. Even so, that last mile, the same thing where if you need to go to Miami, you can take the train there, but when you get there, you have to take a bus or walk or something. And sometimes there are no buses to take, so you have to walk or take a bicycle. So that the technology is actually, to me, very specific to that we need to hopefully develop to the point where that it's available for different size crafts. Similarly, as Scott mentioned, the telecommunications, it would be so great if we can have telecom as a service for those of us flying in low Earth orbit, and then expanding it out, taking advantage of, say, Capstone and all the other missions that are going forward. From the point of view of the capabilities that we are trying to build, that there has to be this kind of sustainability, the ability to get to the place, the ability to continue to make the improvements to our technologies, and then to have, of course, the support of our mission directorates towards these goals. Did I answer your question?
Yes, I think you did. Yes, thank you. And we've been receiving some questions from the audience. So for all the audience members, feel free to send in any of your questions. We'll definitely try to get to as many as possible. One of the first question, and I'll open this up to all the panelists, feel free to respond. The question is, the current standards for construction and testing are for large satellites, such as geocom satellites. What do you recommend as a standard for small satellites?
Well, I'm happy to comment quickly on this.
Yes, please.
So for small satellites, I think that building in multiples is a great idea, and at least 2 or more. It's usually actually the comment about what's done for geos. If there are geo programs, I've worked on a couple when I was in industry, where it is always helpful to have multiples being built if you have 1 or more at a time, because that way, for procurement, for testing, if something goes wrong, you have 2 sets of things to keep schedule with. By swapping one out, maybe one's delayed and everybody kind of works through that. I think the same is very, very true for small satellites, only that should be the default, not the bonus, right? You should budget and plan to build 2 or more at a time, just because the hardware is the least of your costs. The people time is your most expensive cost, usually on a CubeSat program, and every piece of hardware that you bring in or procure really is just trickle down people cost from the vendor coming to you. True for big satellites too. Sometimes the hardware actually has a little bit more value there, but the budgets for CubeSats are small enough that this is more feasible. And having kind of both hardware twins of your satellite on the ground for testing and for on-orbit operations and engineering model is super helpful. And increasingly, we're developing higher fidelity models of our subsystems, and CubeSat subsystems sometimes are very complex, but are sometimes pretty straightforward. And the more straightforward ones are perfect candidates for having these virtual models of them that can be updated with the correct properties and help you get through what the hardest part of any program is, and that is making sure the software all works. So, so if you can have either a physical twin for procurement and schedule, just having a buffer there, and then having a digital twin to get you through that software pain, that would be my preferred structure. If I were granted from heaven a CubeSat lab that I could, and a budget that I could just structure any way I wanted to, that's what I would do.
That sounds awesome. Dr. Rafkin, I think you had some comments.
Yeah, I'd love to add to that. And I think there's no correct answer to that question. I think it really has to be done often on a sort of case-by-case basis. I think the current environment for small sats is the thinking that one of the what makes them so appealing is that they are relatively inexpensive, and part of what makes that happen is that you're willing to accept some level of risk and single string type things, class D type implementations. And in those cases, I think it's appropriate to relax some of the very stringent requirements that we typically put on primary missions, because it is exactly that makes part of this so compelling and so appealing. On the other hand, I think we're going to very quickly see cases where these satellites are really of primary importance. For example, NOAA is considering small sats, constellation of small sats, as part of their operational observing program. These will become essentially at some point essential elements of the Earth observing system. And in those cases, you do want greater reliability. Now that may drive the cost up a little bit, but I think you have to really look at these things on a case-by-case basis and assess where you want to be in terms of science return, operational return, in terms of cost, programmatics, and so forth. And there's no single answer to this, I think.
Yeah, absolutely. And especially for some of these that are constellations, when you talk about reliability, maybe it no longer becomes really the reliability of the individual CubeSat or microsatellite. It's now the reliability of the constellation. And so now the requirement perhaps isn't on the individual one, but really on the capabilities of the constellation. And so maybe individual ones maybe will fail more, but there's other things in place so the constellation continues to, be intact and be able to provide its function. So it definitely changes the way that structure. And I came from the geo world, so the idea that something would fail is just, it's very unacceptable. And it's something that even as an engineer, you're like, I'm going to build something that can fail. Like it's a very hard thing to also switch your mindset into this, into the microsatellite world and sort of let go of that in order to be able to accomplish more. I also wanted to ask, and really any of these questions, anybody can jump in, even if they're directed at anybody, feel free. I wanted to ask you guys actually something near and dear to my heart, which is launch. We talked a little bit about the launch equation, and this is something that, we're very excited here at Virgin to be able to provide these sort of opportunities to be able to get to, as Dr. Cahoy said, where you want, when you want, how you want, and hopefully reduce the time it takes to get to the location where you're going to do your science. So in terms of that launch equation, what do you guys see as sort of like your bottlenecks, your problems? What can help solve the launch aspect? And the answer really can come from anybody, and it can come in the form of, do you need, is it schedule driven? Is it cadence driven? Is it the capabilities of the rocket in terms of when you get here to the clean room, how we protect your satellite, sort of any of these phases of launch procurement and launch, sort of what do you guys feel are some of the challenges that you guys are facing? No problems?
Well,
We're good?
I have one comment, which is one of the nice things that that we've had available for CubeSat programs is working with the NASA CubeSat Launch Initiative effort as a university. Their flexibility in allowing teams who have had schedule challenges for one procurement or component or testing aspect or another to reallocate them to different regularly scheduled launch opportunities is super helpful. It's really hard and stressful and expensive for teams to try to hit an exact launch delivery time. We've had to do that too. And there's a lot more pain. Anyone who's gone through that obviously knows what I'm talking about. There's a lot more pain when you know the day doesn't move. It usually slips to the right a little bit incrementally, but if you know that that's it and game over if you don't make it, that's a hard thing if you miss your rocket. But if you have a system where you have a contract and you have a slot, but that slot is reallocatable depending on how things are going, that is really great for small sat development and for research programs in general. And then, like you're saying, being able to get to the orbit inclination and the orbit planes that you need to get to, whether from an air launch or a space tug, or however somebody else with a big gas tank gets you there, is ideal.
Perfect. Any other comments?
I'll just add, LunaMap is manifested on SLS Artemis 1. The primary payload is the Orion capsule. So we're beholden to the wants and needs of the Orion mission. And if we could have our druthers, we would be dropped off in lunar orbit. But instead, we're dropped off after the Orion capsule is separated. And if we don't execute our propulsive maneuver on time, we would wind up in orbit around the sun, which is the stage that we're mounted to. That's where that will end up, and that's the intention of the Artemis 1 mission. So, as we don't have any issues with that, but if you're at the scale of a very, very, very small satellite, you have to be able to work with the primary payload and work within whatever their wants and needs and desires are to make sure you can still execute your mission. So I imagine for planetary missions, that will continue to be the case. There will always be a primary spacecraft that's launching these smaller payloads, unless we're talking about larger ones, which is if it's its own devoted launch, then that's a different story. But if you're a rideshare, Marco also deployed well before they got to Mars and needed to execute several trajectory correction maneuvers on the way, which was a great demonstration of the ability of a small, very, very small satellite to do that. But if that, I don't know the drivers for that, but it's a similar situation where if these very small secondary ride shares are allowed to deploy, say if you're going out deeper into space, I would suggest that you could even get away with a 6U if you can communicate directly with a mothership that then sends your data back to Earth. So the communications problem that was mentioned earlier may not be as large of an issue, unless you're your own devoted launch, and then you do have to be responsible for all that on your own.
Yeah, I totally can understand that. And I think
so
oh, go ahead.
Oh yeah, so to add to the discussion here, it's the launch for small spacecraft, as I mentioned, the access to space is certainly key, and the ability to not just get to the place where you can precisely inject to the place that you want instead of just fly by like the Marco spacecraft. You're gonna need the new types of maybe lower swap propulsion, etc. But the other issue being a small spacecraft, which I think people haven't mentioned here, is what the small spacecraft secondary does to the primary. There are issues, for example, such as planetary protection. If you're going to Mars, how are you going to affect your primary? Those issues also probably are, they're not barriers, but they will add to some sets of problems that come along with a ride. Not just because you're going to be dropped off at bus stop number 5 instead of number 1 like you want, for example, to go to the moon. Those things, there are multiple issues within getting a small spacecraft to the exact precise place that you want to get to. So the trajectory requirements is one. And there are other issues, for example, like accommodation, how the small set, not everything is a CubeSat, of course, is that in itself needs to be carefully investigated. And I ran a access to space workshop in with Johns Hopkins University Applied Physics Lab this year. In February, and this week we just released the report on the issues, the barriers to get to space, including the launch vehicle as one of the issues. So please go read it. This is a plug, I guess.
Yeah,
Thank
it's
you.
a great report. Thanks for sending it up, Florence. We read it and I sent it to my lab, so thank you.
Yeah, same here. I definitely enjoyed reading that, and there's a lot of interesting solutions too. Especially as you mentioned, the one that really caught my eye was the high cadence. As the launches gain that high cadence, hopefully they'll also help to address a little bit of what Dr. Gahoy was talking about, that, you know, you're trying to target the specific slot. And the reality is even GEOs that have a very, you know, a much more standardized process than something that has, you know, a mission unique instrument often don't hit their time slot exactly. So definitely these CubeSat missions need a little bit more flexibility and given the schedule. So hopefully that it was a very interesting report to see a lot of those findings are really echoed throughout the industry. And also, I know there was an audience question about the current standards for construction of the larger satellites. And I know that Ms. Tan did respond that NASA has a tailored Class D in place for 7120.5 missions. So for that audience member, just wanted to give you that answer. And then we only have a couple of minutes left. So I wanted to turn it over to each of our panelists again to see if they had any closing remarks. And I'll go in the same order again. If you could take like a minute and a half to kind of wrap up any thoughts from today's talk. Dr. Gahoy, I'll start with you.
Okay, great. I was just thinking about your last comment about the construction. And we have an effort that our students are having a lot of fun with at MIT, working on in-orbit assembly and construction of CubeSats, because if you can do that, you can get a higher volume and quantity of components in space for lower launch costs. You can pack things more tightly, and you can also customize them on orbit as needed, kind of on demand. Like if you know you need 20 versus 40 versus 60 versus 100 watt-hour batteries, you can stack them, or prop units with modules for prop, or certain bands of sensors that you need to deploy to replace something in a larger constellation that we're all kind of working our way towards. So I love the idea of kind of compact CubeSat, small sat assembly in space. And I think that's a great new area to take a look at. And it kind of goes along with maybe some of the space tugs or flying parent craft that can deploy them into the right orbit inclinations. So all of these things sound like a lot of fun to me. So just to close with something that I think is fun and exciting that we'd love to see industry or government support to work on, that would be one of them.
Yeah, that sounds really exciting. I think when I first started working GEOs, I got there and, you know, you build it and then you instrument it for vibe and acoustics, and then you take it all apart after testing and you instrument it now for TVAC. And then, you know, you take it apart and you rebuild for flight. And I was like, we keep taking this apart. And everybody was like, oh, if we only built it once, we'd be done in half the time. And so we always joked about how building in space would actually save all this testing that is designed to make sure that you survive launch and not necessarily survive your mission. So that's a fascinating aspect. Thank you for bringing that up.
Yep, survivors of geo industry. Survivors of geo industry, yes. Inspired.
Exactly, we're recovering geo participants. Well, thank you. I'll turn it over now to Dr. Hartgrove for any closing remarks.
Sure. Yeah. I just say I'm extremely excited about the possibilities of, you know, small satellites for planetary exploration. One thing that, you know, we had discussed was just, you know, what is a small satellite? I think, you know, the title of this panel is small satellite, and we've discussed sort of a bunch of different sizes. And I personally feel like there's room in NASA's planetary science portfolio for all different sizes. So everything that, you know, Scott mentioned and Florence mentioned about the larger or sort of upper end of that tier of small satellites, I think is absolutely true. And there's absolutely room for those, and there needs to be continued support for them. And I just think there are opportunities for these types of satellites throughout NASA's mission portfolio. So all the way down to, you know, these sort of 10 to 20 kilogram satellites like Marco and Lunamap and others that are launching on Artemis 1. So I think it's a really exciting time for these types of spacecraft in planetary science. And I hope that everybody out there can keep thinking about new and novel ways to do interesting science in the solar system with, you know, with spacecraft at all these different size scales. So, thanks for having me on.
Yeah, thank you. Yeah, I think that's a great point. I know that when I was a kid, I remember watching Sojourner land on Mars, and I was so excited. And I asked my mom, I was like, when's the next one? And she was like, oh, it's like years away. And I'm like, I can't wait years for the next mission. So I think that, you know, what you touch on is really interesting about, you know, having these become more frequent and the possibilities that CubeSats offer in that area. Dr. Rafkin, any closing comments?
Yeah, thanks. First, thanks to Ascend and Virgin Orbit for the opportunity to participate in the panel discussion. It's really been great, and to participate with my fellow panelists. I don't have a lot to add. I think there's been a lot of really great stuff discussed. One additional issue that came to mind that I'll just bring up very briefly is risk and risk perception. You know, the reality is missions only fly if they get selected. And a major hurdle to getting to that selection is the technical management and cost review. You know, Florence mentioned that there are standards for Class D missions, sort of these higher risk missions. But I think the novelty of small sats and small instruments and their recent arrival sometimes clashes with the long culture of risk assessment on the TMC panels. And I don't know that there has quite been that paradigm shift of accepting lower risk for these, or accepting higher risk for these typically smaller, more risky missions. I think that's going to change in time, but it's going to take a community of us to facilitate that shift, both from the proposers, from the launch providers, from the small satellite bus builders, and even from NASA itself to you know, to educate the TMC panel that they rely on to provide guidance on selection. So I'll leave that part of it there. I think we're still in the middle of that paradigm shift, and we needed to get it sorted out. Overall, though, the future's bright. The technology's there. I think it's going to continue to advance rapidly. The programmatics really are in place, and the science demand is there. And I think the revolution has begun. It's going to be a great ride. Within the next decade, I think small satellites are going to become increasingly common as ride-alongs, but also as their own standalone missions in their own right. And we will see small sats enhance primary missions, and we're going to see them as their own, I think, eventually their own prime missions, perhaps even flagship class missions of a fleet of small satellites. These are all possible. So thank you all. Thanks for your virtual attendance. Sorry we couldn't do this in person, and thanks for your attention.
Thank you so much, Dr. Rafkin. And I agree, that sounds so exciting. And I know from the launch vehicle perspective, especially having come from the satellite side, we are so excited about all these potential missions. It's so many things are in proposal stages or already in building stages, and we're really excited. I really can't wait to house them here in our clean room and get to know all of the missions a little bit better, because they're incredibly capable. And there's a lot of exciting science there. So I hope, like you said, that there's that shift for more acceptance, it's going to happen. So I hope it does happen sooner rather than later. We'll definitely be pushing for it. So I'll now turn it to Ms. Tan for closing remarks.
Hi, and thank you again for hosting this very interesting talk and panel. I enjoy my fellow panelists very much, listening to them. So certainly there is a place for small sats for decadal class science, exploration, innovation. And I look forward to, I guess, keep trying to reach out to my fellow panelists and talk to them, because it's so exciting that I'd like to do this one again, you know, at a smaller group. So there is an interesting shift even today, right? We've gone from CubeSats, and now the ESPA class spacecraft, like Simplex, for example, those things are maybe 90 to 200 kilograms. And so these mini satellites are going to be more and more used for these decadal class observations. And these data products from the large or small missions will eventually become indistinguishable in some ways, right? And the ability to even meld the data from multiple sources might be also interesting, not just our NASA science, but say from industry. Our business model has been, vertically integrated in the past, and to build and custom build and make this bespoke spacecraft that we launch. And there's another area where we can buy data as a service from places like Planet and all the other data companies. They're not spacecraft companies, they're data companies. But there's all this territory in between. And so how we use that, think about the next business model of how we use the data, the industry, which service we buy, which products we buy, and what we field. It gives us the chance to really deploy our R&D dollars very smartly, I would say. And of course, the new insights that we get from multi-instrument constellations with data, machine learning, data fusion, analytics, is going to be very insightful for the future. And that synergy between large and small spacecraft is going to continue to grow. We as a group, NASA, should be thinking about, of course, international cooperation with our key science communities, and that we should certainly learn from each other and collaborate. In thinking about access to space, the dollar per kilogram likely will fall. We can perhaps use the different multiple launches that are going up. For example, the Starlink satellites. If there's an opportunity to be a hosted payload there, that can also be an opportunity. Or different other communities that are producing opportunities for us to get to the places we need to get to do our science. With that, I close. Thank you for your time, and thank you so much for hosting.
Thank you so much, Ms. Tian, for your closing remarks. And I want to thank all the panelists for your amazing work that everyone is doing, both on the small sat side and on the NASA side. And thank you so much for taking time out from that important work to talk to us. You guys are definitely leaving us convinced that the future is bright, and it's, and microsatellites are part of it. So thank you so much.
Thank you, Shandy.
Thanks.